I'd like to introduce myself. My name is Nichole Price. I'm a senior research scientist here at Bigelow Laboratory for Ocean Sciences, and I also direct our Center for Seafood Solutions. Bigelow Laboratory is a nonprofit research institute that studies the foundation of global ocean health and unlocks its potential to improve the future for all life on our planet. I started at Bigelow just over 6 years ago, and I've really enjoyed my time here and having the freedom to explore the scientific questions that intrigue me the most. And a lot of those are now around solutions-based science. So I'm really excited to give you this presentation tonight. As a nonprofit research institute, the discovery, solutions, and inspiration we create are made possible with the help from the support of our generous donors, like Andrew Davis and the Shelby Cullum Davis Charitable Fund that supported a lot of the work you'll hear about tonight. I want to start by thanking each of our donors, board members and advisory board members for their support too. I'd also like to extend special thanks to H.M. Payson, a Maine-based financial advisor that is again sponsoring this series of talks. Please use the question and answer button at the bottom of your screen to send us questions as I go through the talk, and I'll try to answer as many as I can at the end. And we'll take a break partway through too. You'll also notice a raise hand and chat button, but those features aren't available for this event. I can't even start this talk without first recognizing that this work is the result of a large team effort across many institutions. A small group of us launched this effort a few years back with some funds internal to Bigelow and an idea. That idea and the funding support grew and grew over the past 2 years to include many scientists from different disciplines and institutions to tackle a critical question. And that question is, can we use algae to reduce a cow's carbon hoofprint? What is a cow's carbon hoofprint? Well, first we need to understand that cattle contribute to 62% of the livestock emissions. So they're a big component of the livestock emissions. And that is about 5 gigatons of carbon dioxide equivalent per year. That's quite a bit of greenhouse gas emitted from one sector. Most of those emissions are from methane burps from the cow, or enteric fermentation. So you see in this diagram, that whole purple piece, the 44%, which represents the greenhouse gases coming out of livestock production, is from methane burps. And if you break down the other pieces of this diagram a bit further, you see that there's contributions from manure, energy consumption to make beef and milk and all the other products that come from raising livestock. And then some of the carbon footprint from generating and moving around the feed. Why are we worried so much about methane? Well, although methane persists in the atmosphere for far less time than carbon dioxide, only about a decade, it's much more potent in terms of its greenhouse gas effect. In fact, pound for pound, its global warming impact is 25 or 28 times greater than that of carbon dioxide over a 100-year period. Globally, it accounts for approximately 16% of human-generated greenhouse gas emissions. So methane, in and of itself, is a pretty important or potent greenhouse gas, but it's also a precursor to ozone, which is an additional greenhouse gas that causes warming of our planet. So methane, when combined with sunlight and other nitrous oxides, can create ozone as well. So how do cows make this methane? There's common misperception that it might come from this end of the cow, but in fact it comes out of this end. It's burped out of the cow. And cows burp methane from the rumen during their natural digestive process. So there's microbes in the cow's stomach that break down the kind of tough fibrous feed that they eat to glean the usable energy and protein from that source. However, part of those microbes, or about 5% of the microbes in the gut, are of a type called methanogen. And these methanogens are the ones responsible for creating the methane that gets burped out. Cows actually lose energy by making methane. So it's not necessarily a good thing that they're making methane. It's a necessary evil to really carry hydrogen gas out of the cow gut and back into the atmosphere, so you don't have a gas buildup in the rumen. But methane does represent from anywhere from a 6 to 12% energy loss for the animal. And so if you can reduce the amount of methane that the cow is burping, you can actually increase production of both milk and beef. So what are the current livestock methane mitigation options that people are employing today? The first steps that have actually been implemented over the past 40 years or so is first to improve feed quality and animal breeding to enhance the feed conversion efficiency per cow. And that means you need fewer animals to produce more meat and dairy. And more recently, people have become very interested in rumen microbiome manipulation. So the rumen is that foregut where the the fermentation and digestion process happens, where the methane is created. So if you can manipulate that rumen microbiome, you can disrupt the production of methane or methanogenesis. And the general idea is to inhibit that methanogen population. And there are actually some products already on the market or are on their way to market. One of those is Nichole, another one is called 3-NOP. I'm sure many of you have seen the ad that Burger King put out purporting to use lemongrass for the same purpose. And each of those targets about a 30% suppression of the methane burps from the cow. Other approaches are using just antibiotics in cattle to reduce that methanogen population. But it turns out that might affect the amount of methane that comes out from the manure downstream of the cow, so to speak. And so these are some of the solutions that exist. They're not all perfect. Some of them aren't supported by scientific evidence quite yet. But we and many others have been starting to ask the question, can algae suppress methane burps? And so what I'm showing you is some work that was done by Machado for her dissertation back in 2015. And she started looking at a green alga pictured on the bottom and a red alga pictured on the top, and fed those, included those in an in vitro assay or a benchtop assay, where she tried to see if it could affect that rumen microbiome and the amount of methane that was getting created. And what you can see, if I can just move my mouse around here, is that for the places with the plus A, or you can barely see them, they're the bars along the bottom, that's where the Asparagopsis taxiformis was included. There was 99% less methane emitted from these benchtop trials. So that's pretty shocking and pretty exciting. And how is this happening? Well, the algae were disrupting that methanogen activity and were, in fact, reducing the methanogen population. So these bars show 3 different grade colors. Those are 3 different methanogen types. And then when she fed Asparagopsis, denoted by the ASPs there along the x-axis where the red arrows are pointing, you can see the reduction in that methanogen population. You should also note these other bars that show a reduction in abundance of methanogens. Those all start with a B of some form, and those are positive controls which contain a brominated compound. Now, the reason that Asparagopsis was tested and is so excited is because it stores this antibacterial brominated compound in glands in the cells. This is a natural process that Asparagopsis does to prevent fouling from the younger life stages. So although we could see this effect of Asparagopsis in bench trials, obviously the next thing you want to do is test it in live animal trials. And so there's a series of these experiments that have been done now by other folks using Asparagopsis. And when fed to sheep at really low inclusion rates or really low proportions of their diet, only 0.5 to 3% of their diet, or to beef cattle at extremely low concentrations, and dairy cattle also at low concentrations, we see that there's in live animals a 50 to 98% less methane produced by these animals when fed a very small amount of these seaweeds. So that is pretty exciting because seaweeds are actually more effective at methane reduction than some of these other feed additives. And here's just a table showing the relative differences with some of these other options. Lemongrass isn't on here, and neither is Nichole because they weren't published about quite yet at the time of this study. So while I'm the director of our Center for Seafood Solutions, in that capacity, I sit on the Maine Seaweed Council, and when that paper came out in 2015 and another in 2016, I started getting a lot of questions whether Maine seaweeds that are already actually used in animal feed, can any of these suppress enteric methane? And so that's when we started pulling this team together to answer that question. And as we've broadened our considerations about how algae may be used as livestock feed, we've thought of a list of criteria that we think are important to research in order to identify the perfect set of candidates for livestock feed supplementation. And so there's a list of 6 options here on your screen: algae selection and suitability, algae production volumes, environmental sustainability of algae production, profitability for algae and dairy producers, animal and consumer safety, and health or quality co-benefits of algae animal feed. And what we're going to do is launch a interactive section for you guys. You can vote in the little pop-up you've just gotten on your screen for what you think among those criteria might be the most important part to pursue in order to gauge algae's suitability as livestock feed. And we'll just leave this running for a little while now until we get the votes in, and then I'll share the results of that vote with you. But in the meanwhile, I want to invite you also to use the Q&A button at the bottom of your screen to ask any questions that you have thus far in the presentation, or if you look at that list of criteria and think there's something terribly missing from that list, I'd love to hear about it too. So we'll just give this a few more seconds. I think the numbers are really starting to settle out now. So I'm going to end the poll and share the results with you all. So you can see here, algae selection and suitability and algae production volumes aren't a big concern relative to the environmental sustainability of algae production, and the profitability, safety, and any other co-benefits that could happen from using algae as a livestock feed. Well, never fear. We're going to review all of these potential criteria for the remainder of the talk, so you won't miss out on an opportunity from hearing about how we're thinking about each of these. But in the meanwhile, if there are any questions, I'd be happy to entertain those too, and the Q&A button is right at the bottom of your screen.
Great, thanks, Nichole. Our first question is, do cows need methane? Why do they have methanogens?
Yeah, it's a curiosity. In truth, I don't know how certain we are that they absolutely need methanogens and to produce methane, but it is used as, again, as a way to carry hydrogen out of the gut. And in fact, for a lot of these feeding trials, when you see the reduction in methane emissions from the animals, you actually see the production or increased production of just straight hydrogen gas. So they have found a way to continue to get rid of that hydrogen gas and prevent gas buildup just by emitting hydrogen gas rather than methane.
Thanks. Our next question is this a solution that fast food companies will have access to? If so, should we be worried about an overharvest of algae?
I think that's a great question. Clearly, Burger King is thinking about implementing solutions. I was part of a workshop last November that was hosted by the Department of Energy, the World Wildlife Fund, and the Foundation for Food and Agriculture Research. And we had a lot of major end users participate in that workshop, including McDonald's, Cabot, Tillamook, Stonefield, some others. But so there are definitely bigger producer or bigger product makers that are very curious about this process. And for that reason, a lot of us are thinking very specifically about using aquaculture approaches to address algae production needs specifically so that we don't end up over harvesting any particular species from the wild.
Great. Next question is, haven't cows always made methane?
Yeah, they have always made methane. There just hasn't always been quite so many cows on the planet. So I think that there are now about 1.5 billion cows on the planet, and that definitely wasn't the way the Earth was pre-industrial period. So while they've always been here, they've always burped methane to some degree, it's not necessarily been at the volume that we're looking at now.
Our next question is, to what extent do animal feeds already include algae?
That's a really good question. So at least in the organic dairy sector in the Northeast, over 50% of the dairy farms organic dairy farms are using kelp meal in their diets. And I think in the Midwest, the numbers get even higher for organic dairy farms. Up to 80%, I think, use kelp meal in their diets in some of those Midwestern states. So it's not at all a novel idea to start including algae in cow's diet, but it is novel to think about doing it purposefully to also suppress methane at the same time as providing nutritional benefit to the animal.
Thanks, Nichole. Next question is, what is the mechanism that algae uses to suppress gut methane production?
Yeah, I alluded to it. We know for the Asparagopsis, they have those glands that concentrate the brominated compounds. And they do that because those brominated compounds can prevent the alga from getting attacked by other microbe species in the aquatic environment. That also happens to prevent methanogen activity in a cow gut. There are other seaweed species that produce brominated compounds as well. It's not only Asparagopsis, and there may even be other bioactive compounds other than brominated compounds that disrupt the methanogen methane creation process.
Thanks. And people can keep their questions coming in, but I think we'll do one more as part of this break.
Okay.
So this question is, why don't we just stop consuming dairy and beef to solve this problem?
Yeah, it's a good question, and one that you should keep in the back of your mind as we move through the talk and think about production needs for algae to meet the demand for that 1.5 billion cattle that are on the planet. So personally, and this is just me speaking, I think that both of these ideas have to meet in the middle. That there are going to be people who continue to choose to live a vegetarian or a vegan diet. There are people who don't have the opportunity to select that kind of a lifestyle and just need to find protein. And so if we can apply these tools to suppress methane burps from cows at the same time as perhaps reducing our consumption of dairy and beef, that's probably the answer that the globe needs to seek. And with that, I'm going to move on to walking through those criteria and telling you how we're considering each as we develop our research program. Okay, so criteria number one was which alga to use. So obviously we started off this talk talking about Asparagopsis because it can be such a good storage vessel for all those brominated compounds, but it's also notoriously difficult to cultivate. So Jennifer Smith at the Scripps Institution of Oceanography, who was my postdoc advisor before I came to Bigelow, has been working on finding different cultivation techniques for Asparagopsis that try to maximize biomass yields and performance. But even she would say it's going to be a while before we can imagine scaling that up to where it needs to be. It's also difficult to source, even for these live animal trials from the wild, because in any one location, it won't be necessarily as abundant as you think in order to get get enough for the trials, and it's also a very filmy sort of alga, so getting a lot of biomass is challenging. But on top of that, Asparagopsis is an invasive species, so I personally also don't want to see motivation for ocean cultivation of Asparagopsis in particular. So then where does that leave us? Well, I would like to see an alga that is native, that can be produced sustainably at a reasonable scale, and produces sufficient amounts of bioactive compounds to be effective against methane emissions from cow rumen. It has to be safe and have nutritional value in and of itself. And it might be a microalga like phytoplankton, or a macroalga like seaweeds, or a blend of the two that is the answer to which alga. We've started tackling this problem. So Steve Archer and Kevin Postman had a paper out with others last year that described a technique to test for the ability for microalgae to make brominated compounds. And we have some early results from species that hadn't been tested before. We've used that same assay to test the ability for different macroalgae species to make brominated compounds, and have some species that we're excited to continue considering and testing in our in vitro trials at Bigelow. But any of these species have to be scalable. Now, let's think about this issue of scalability for just a second. And because we're in Maine and this research is focused on some of the Maine sectors here, we'll just take Maine as an example. It's a good test bed. So Maine has 28,000 dairy cows as of January 2020. And assuming that each cow eats about 20 kilograms dry weight of food per day, and let's ballpark a 2% inclusion rate of seaweed to be fed to each of those cows. So that means you need 146 kilograms of seaweed per cow, dried seaweed per cow. Seaweed's got a lot of moisture content, so that's actually 584 kilograms of wet seaweed per cow per year, times that 28,000 cows. That leads to 16,352 metric tons of seaweed landed just for dairy. That's not a small amount of seaweed. Well, let's look at what Maine produces for seaweed. So here's our seaweed landing and value history from the Maine Department of Marine Resources, starting back in the 1960s and going up through 2018. And you can see that in 2018, we were just about 11,000 metric tons of seaweed landed. So in fact, we're not too far off from producing the amount of seaweed we need to address the dairy cattle in Maine. But at a global scale, that's going to be a much larger number. So how do we scale up production of macroalgae and microalgae to meet that kind of demand, specifically through aquaculture techniques? Well, the Department of Energy has invested over $25 million to support 18 teams to develop tools and technology for scaling up offshore seaweed cultivation for lots of purposes. And biogas in the future is one of them. But animal feed can potentially be a preliminary purpose for the seaweed until that biogas market makes sense. What about microalgae? How easy is it to scale microalgae production? Well, Nebraska just, there's a microalgae company that just got started in Nebraska that makes fish-free omega-3 fatty acids, enough to compete with 15% of the global salmon fishery. So they just broke ground on a $200 million facility, and they can produce a lot of microalgae. USDA also has recently supported a $10 million award to look at microalgae as chicken feed. So we're talking about cows today, but people are thinking about algae for feeds for all sorts of animals. Never mind land livestock, but sea fish as well in aquaculture pens. So we do think we can scale seaweed production and microalgae production, but is it environmentally sustainable to do so? And I want to pay special attention to this, since from your poll here, it's clear that this was a major concern. So we have recently been doing work at Bigelow and with friends from UNH and University of New Hampshire and from Island Institute that's demonstrating that seaweed aquaculture restores water quality. It adds oxygen to seawater as a byproduct of photosynthesis. It absorbs carbon dioxide, which can temporarily and in a very local area mitigate the problem of ocean acidification. But it very well may also sequester carbon, and there's a lot of new science that's happening around this particular process, and I'd be happy to answer questions about that later on. Seaweed naturally absorbs lots of nitrogen and phosphorus as it grows, which can mitigate nutrient loading from land inputs to the sea, or a process we call eutrophication. And to make seaweed via aquaculture or microalgae, it uses very little fresh water, very little nutrients, and definitely less tillable land than our land-based agricultural crops. And in the ocean, it can provide nursery habitat for other commercially important species or just ecologically important species as well. Seaweed aquaculture rather than wild harvest is a growing industry. So here are some data from the Island Institute Edible Seaweed Market Analysis that show the relative ratio of farmed in orange to wild in gray edible seaweed harvest in Maine over the past 5 years or so. And this trend I'm showing you for Maine, but it is replicated around the globe, where rapidly aquaculture of seaweeds is going to surpass wild harvest in very short order. What's very cool to think about for Maine in particular is that seaweed aquaculture and processing are really in close proximity to each other and to organic dairy in Maine. So this is some work that some Colby students have been helping me with this summer and have done a nice job with, but they've mapped out where there are aquaculture sites that include permits for seaweed farming. I want to be very clear here. Those dots on the graph or on the map on the left show where seaweed is permitted to be farmed, but it's not necessarily where seaweed is actively farmed currently. It's a much smaller fraction than that. Probably only 20 farms are actually farming seaweed. Then the orange dots in the middle map are showing where the seaweed processing facilities are, and then on the far right map you see where there are organic dairy farms in Maine. So if you want to think about cradle to grave, what producing seaweed means and what carbon footprint it has in and of itself, when you can take it so easily from a coastline and move it right to your users, then you've lowered your transportation carbon footprint. And then you can think about microalgae production in places like Nebraska or elsewhere in the Midwest to meet the demand for those interior states. Okay, so I hope I've answered that sufficiently for those who had that concern, but of course we can come back to questions at the end of the talk as well. So criterion number 4 was profitability. This, I think, is actually where some of the most critical questions need to be asked and answered. So after growing, producing, culling, drying, milling, and packaging your seaweed and all the associated capital and operational expenses along with it, farmed seaweed can be as much as 10 times as expensive as a wild harvested product. But I think we're all aware that dairy margins right now, especially right now, are quite thin. And so it's difficult for dairy farms to remain profitable as well. So you have two industries, one just starting and trying to gain a foothold, and another worried about maintaining profitability, trying to meet in the middle. So just to kind of spell out how complex this situation is, this diagram here, which I don't expect you to read in great detail on the right, shows all the different parts of the supply chain, from the nursery production of seaweed seed all the way down to the consumers of what could be considered a blue milk. And we don't even know how much or if people are willing to pay a higher price point for milk that has a lower carbon footprint. And we've just started playing around with numbers, knowing what an average gallon of organic milk costs, and trying to figure out what relative change there would be to that cost with these seaweed inputs. So don't take these values on this graph as being fact. We are still working on this. But we do fear that there could be a big gap there. And so one way to think about how both could be profitable is to realize that multiple products can come from a single crop of seaweed or of soy, as you can see in this simple flow chart. So in soy production, after it's pressed and then the oil is used for one product, you have the leftovers from the pressing or the residue that can be used for soy meal or other products that maybe have a lower value but still bring revenue. The same could happen for seaweeds that could be processed for one higher value product, and the residues or byproduct could be used for an animal feed. And this could increase efficiencies and allow for higher value co-products to be sold from the same crop, thereby meeting the profitability needs for seaweed. So I want to stop for a second and just remind you what microalgae and macroalgae are used for already. So what are some of those other high value products? Well, animal feed is the one that we're considering today, and that wouldn't necessarily be a very high value product. And other low value products coming out of macroalgae or require a lot of biomass to make are stabilizers and emulsifiers, fertilizers, which can be sold as organic and then get a higher price point. It can be used as a feedstock for biogas production in big anaerobic digesters, or it could be used directly as a biofuel. It's already used for food for people and supplies minerals and vitamins for humans as well. We're getting a little bit more excited about the potential for microalgae, maybe macroalgae, to be used as an alternate source for plastics or bioplastics. And then there are the nutraceuticals, pharmaceuticals, and cosmetic industries, which probably can charge the highest price point for algae. So there's a lot of algae production already happening, and a lot of places where we might consider peeling off for livestock feed. Safety. Safety is something that always needs to be considered. And should you feed kelp to your livestock? Well, there are certain things that we need to be aware of. Seaweed is naturally very high in iodine, and because seaweed is really a sponge of the ocean, it can absorb metals that are naturally found in seawater. It may affect palatability and intake rates of livestock. And then there are the brominated compounds like bromoform that could be present in seaweed. All of these things need to pass through FDA certification and GRAS certification, which is generally recognized as safe. So let's take these one by one and talk about how concerned we really are about any of these potential problems. So iodine is found in a lot of foods that we eat, and it's probably true that the American diet, especially as people have been trying to reduce salt and iodized salt, is a little bit deficient in iodine, if anything. But like most things in this world, you can have too much of a good thing, and there are limits for iodine consumption. And when cows are fed kelp meal, they can approach some of those recommended iodine limits. But I think that with careful consideration about which seaweed species you use and some preparation techniques, you can walk away from that iodine concentration problem. Another thing to consider is arsenic. So total arsenic concentrations in seaweed is naturally high. This map shows the increasing concentration of the given of arsenic, in this case total arsenic, with the increasing size of the symbol, and the highest levels of arsenic are found at site 10. And the high values in this area of Maine in particular are predicted to be due to the vicinity of Hancock County, which has high arsenic leaching into well water from bedrock. This is just a natural process. This natural source of arsenic could be impacting the seawater and seaweed in the area. Site 10 is also located in the area of the historic Callahan mine, which excavated ore containing arsenic during the 1970s. So on the bar graph, the dotted blue line and red line brackets the values of arsenic previously recorded in studies of the area. And the concentrations of arsenic that we found are generally a little bit greater than previously found, which encourages us to want to look further into arsenic speciation. I'll explain that in a second. The black dotted line there at 3 micrograms per gram represents a concentration or an international suggested regulatory limit for consumption of arsenic in food products. It is really important to note that arsenic is only dangerous for human consumption when in the inorganic form, not when it's in the organic form. So here are arsenic levels that you can find in lots of other common foods that you eat. And then I really want to stress again that arsenic levels are only matter when you're talking about the inorganic form of arsenic. And all of the Maine kelp that we've tested so far is less than 2 micrograms per gram and well below that very conservative limit of 3 micrograms per gram, which I've read elsewhere is also up to 5 micrograms per gram. So we don't have any cause to be concerned about arsenic in seaweed coming from Maine. Bromoform can be concerning. It's one of those brominated compounds that may act to reduce that methanogen population in the cow rumen and thus reduce methane production. So we have to make sure that the bromoform in Asparagopsis or other seaweeds doesn't harm the cow, doesn't come through the cow into beef or milk. And high levels of bromoform can damage liver and kidneys. So here's that paper that just came out this year from Kinley et al. Showing the really great suppression of methane and the replacement of methane with the hydrogen. And what they also found was there was no bromoform residues in the beef from this cattle. So that's great news. Okay, let's move away from some of the scarier or riskier things you need to think about with seaweed and think about some of the other exciting pieces like health co-benefits. So this is some work from Andre Brito, who's part of our team from the University of New Hampshire. And this is a study that he did with kelp meal, and he looked at pasture intake rates for cows that were not fed kelp and cows that were fed kelp across the summer months in Maine. And there was a noticeable increase in the intake rate when cows were fed kelp. So this is, generally speaking, a good thing from a dairy producer's perspective. They're eating more, they're growing more, they can produce more milk. Other co-benefits that have been identified in the beef industry include improved beef cattle immune resistance to fescue toxosis. So fescue grasses can sometimes have a toxic endophyte found in their tissues. And when the cows eat it, they can become very sensitive to heat stress. But if you feed cows kelp meal while they're also grazing on this fescue, they become much more immune to that toxicosis and to the heat sensitivity. Rockweed or this kelp meal or macroalgae can also improve milk quality and in some cases yields. So this is a paper produced back in 2016 that shows when you feed cows kelp, they have a reduction in something called the somatic cell count. Somatic cell count is a marker for milk quality and udder health. And this dashed line here at 400,000 cells per mil is a cutoff limit for US dairy producers to be able to ship their milk overseas to Europe, for instance. So getting below that 400,000 cells per mil of somatic cells is a really important marker for dairy to be profitable. And so kelp can improve this milk quality. Rockweed or kelp meal can also improve beef quality and shelf life. So this is an older paper now from 2006, but when beef cattle were fed kelp, they had a higher marbling score for their steak that was produced. And interestingly, there's another study that showed that the steak had a longer shelf life after the cows had been fed kelp meal, which is, I don't understand how that works, but it's really interesting. So we have walked through these 6 criteria. We think we can find maybe a blend of algae that foots the bill, that is safe, can be produced at scale, is environmentally friendly to do so, and can offer some co-benefits to the dairy or beef industry. But remember, we started out this conversation today with, can we use algae to reduce a carbon hoofprint from a cow? So I just want to remind you why we started there. And that's because globally, 30% of the methane that we are producing as a globe comes from algae, 30% of the methane we produce from a global perspective comes from livestock, burps, and waste. So this is a huge portion of a greenhouse gas that is a very potent greenhouse gas that if we can find a way to tackle it, that's a big win in the battle against climate change. So let's think about how algae could impact the cattle carbon hoofprint. And I think it might actually be at multiple stages. We spent most of today talking about reducing the enteric fermentation of methane gas, or in other words, changing the gut microbiome of a cow in its rumen to prevent methane burps. And there are some seaweeds that can reduce that by 98%, which is really exciting. We don't know yet if feeding seaweed to the cow or algae to the cow would change anything about the manure and the production of methane from the manure. We also have colleagues who are just starting to figure out whether or not you can use seaweed straight as a feedstock to add to with the manure in biogas generation. We also need to consider that if we're replacing 2% of the cow's diet with seaweed, is that reducing the relative carbon footprint from like soy or corn that has a pretty actually large carbon footprint for production? If we use seaweed as a direct fertilizer, can that help prevent some of the nitrous oxide production from pastures? Or even would it do so indirectly by changing something about the nitrogen content in the manure that the cows are producing that's also landing on those same pastures, or the urine, for instance? So there's lots of places and lots of opportunity for people to do research into how algae could impact the cattle carbon footprint. Let's take it back to Maine now and think a little bit about Maine and what our total carbon emissions are in Maine is about 17.51. I forget what that acronym stands for, but a lot of carbon dioxide, excuse me. Maine's livestock are 1% of that total budget. So it's not a huge carbon hoofprint for Maine livestock, but livestock elsewhere in the world, like for instance in New Zealand, is 30% of their carbon budget for comparison. So this is an important solution that can be applied here and help us in Maine, but help lots of other places in the world. And just to think a little bit more about Maine's annual carbon budget, what we just described is how we could impact that agricultural contribution of net emissions to the atmosphere. But what hasn't been included in the Maine's carbon budget yet is any consideration for carbon sequestration merely by growing seaweed in the ocean, which may also contribute to abatement of our carbon footprint in Maine, or our carbon budget. So to conclude, I think there's a lot of exciting climate opportunities to think about when we're applying algae as a solution to enteric methane emissions, maybe soil health, maybe alternate energy production, but algae could impact cattle carbon hoofprint at multiple stages. Algae can also increase profitability both for the working waterfront and for dairy industries. Aquaculture of seaweed for livestock feed could restore water quality and may even sequester carbon dioxide. Finally, algae cultivation on land or in the sea could act to mitigate nutrient loading. So I hope that I've ended our Café Sci series with a glimmer of hope. And with that, I'd like to really thank all of the important partners we have helping us with this work. Again, the Shelby Cullum Davis Charitable Fund for their financial contributions, and then all of our academic and commercial partners in this venture. And at this point, I'd love to answer any more questions, and go ahead and use the Q&A button at the bottom of your screen to submit those questions. Thank you.
Thanks, Nichole. Great talk. The first question is, are there any large agribusinesses that already have their hands in commercial seaweed or algae production? And if so, which ones?
Agribusinesses, not that I'm aware of. The biggest use and production of seaweed right now is for hydrocolloids, so things like carrageenans and alginates, which are those emulsifiers and binders. But I'm not aware of large production of seaweed for agribusinesses other than fertilizers.
Great, thank you. The next question is just about how the pandemic may have affected this research so far.
Yeah, so if I go backwards just a second here, you'll notice that we have partners in Vermont, New Hampshire, Maine, even Canada in some cases. And so one of the challenges that we've faced is how to get everybody together to continue this research during the pandemic. We've been using Zoom a lot. We were already doing so to facilitate in-person sorts of discussions when it would be too far for all of us to travel and get together. But it has impacted our ability to start our in vivo or live animal trials. We had hoped to start this summer, and we'll be postponing until this fall, when we're very hopeful that we'll be able to get some student help back into the labs and onto the farms to assist with the data collection.
Thanks. The next question is kind of related to some of those things that you were just talking about. How is it that you will be able to measure and monitor the burps?
Oh, that's a great question. I should have included a picture. I'm sorry about that. So there is the method where it's kind of like the Bubble Boy, if you've ever seen that movie, where you put the cow in a giant enclosed bubble and then you can measure all of the methane releases from that animal over a certain time period. But that's, you can imagine that's challenging to put together and might be none too fun for the animal. So we are employing a system called the green feed system. And this is a, in some cases mobile, you can roll it out onto a pasture, but it's a big walk-up piece of instrumentation where the cow can voluntarily stick her head in to feed and the grain that's available for her in there. And while her head is inside, there are sensors that are measuring her exhalations. So it's measuring how much carbon dioxide she's exhaling and how much methane she's exhaling too. And because the cows are wearing something called an RFID tag, they can be, you can record which animal came and how long she stayed, how much she ate, and how much methane she burped out. So it's totally voluntary, and when you are running these experiments, they go for 60 days, maybe even 90 days, and so you get a lot of visits to that piece of equipment and you get a lot of data.
Thanks, Nichole. Next question is, why would algae be better than the lemongrass that Burger King has been talking about?
Yeah, that's a really good question. Let me see how far back I need to go. I think this slide sort of tackles that question. The lemongrass only affects the carbon hoofprint here in the enteric methane fermentation application. It also only reduces the methane by 30%, not 98%. We don't know if that affects manure, but it doesn't get used for biogas generation. It doesn't get used as a direct fertilizer or an indirect fertilizer. And it doesn't replace in a meaningful way anything else in the feed that isn't, lemongrass would also have its own carbon footprint to create and grow. So there's a lot of carbon reasons why algae would be better. And then the other reasons that I alluded to in criterion 6, all of the potential animal co-benefits for animal health. There's many more than I listed there, even that people are curious about or starting to test. And if any of those pan out, then there's an additional, possibly reduced expense for the dairy farmer, and so even more financial incentive to use algae as a livestock feed supplement. Thanks.
Thanks. Next question is there an eventual opportunity to actually require the use of methane reducing feed in the beef industry?
As long as some of the protections that were put in place during the Obama presidency to limit methane emissions at a national level. And as long as places like California continue to consider how to reduce methane emissions, and states like Maine set carbon neutrality goals for the next 25 years or so, then we are on our way to incentivizing. But there could be other policy incentive to include any sort of methane suppressant as a livestock feed. And if there are carbon credits to be had for the dairy farmer, the beef herder, or the seaweed farmer, then there's even more incentive. And there's an opportunity maybe even for nitrogen credits. There's an example of that happening in the state of Connecticut. So there can be voluntary carbon markets or otherwise sorts of cap and trade or tax incentives as well for reducing methane emissions from livestock production.
Thanks. Next question is, are there any health concerns to the cow from reducing its methane output?
Yeah, not so far. I'm sorry, I'm flying back here through these. There we go, this graph. Remember that the purpose of the methane was to carry away the hydrogen gas. And it looks like the cows are able to just instead burp off straight hydrogen gas. So no, it doesn't seem at this point like there's any concern for replacing the carrier gas of methane with the carrier gas of hydrogen. And that purpose is still served by this other gas that is much less harmful to the atmosphere.
Thanks. Our next question is, what can the public do to help?
Well, we are developing a website to allow everybody to follow along in the ups and downs of this project. And we'd love to invite everyone attending this talk to pay attention to when we launch that website so you can see what we're doing. But you can do things like write to your politicians, encouraging them to consider setting methane emissions limitations. And you can do things like donate to Bigelow so that we can continue doing this really exciting research. And if you are at all worried about seeing seaweed farming happening outside your window, consider all of the positive impacts it could have in the fight against climate.